Bismillahirrahmanirrahim. Assalamualaikum and good day. In this video, I'm going to explain on the last part of chapter 2, which is the maximum likelihood estimation for exponential distribution parameter. Before we go through on detail about the estimation, let's go through or recap some of the properties of the MLE, which is it is one of the most robust parameter estimation, and it's also consistent, efficient, and unbiased. So all these four properties of estimation you already learned in the statistical inference subject. So it's just a recap for you. So you can see here that the MLE is very good estimation method. That is why it is frequently used in the application. But from the constraint, so to achieve the properties of the good estimator, so the constraint is the sample should be quite large, which is 30 to 50 or more than 100. So depending on the application area or the type of data. So we should make sure that our sample is sufficient enough so that the outcome of the estimation will be fulfill all the good estimation properties. Okay, next let's go to the general step in MLE. Okay, basically the first step we have to generate or to define the PDF of the distribution. So it depends on the distribution because now we want to estimate the parameter of the distribution. Okay, so and then we have to define which parameter that we want to estimate. Okay, for example, in exponential, we only have one parameter, so we know that it is just a lambda. But for example, we have variable, so variable for two parameters, so we have beta and eta, so we have to decide in advance which one we want to estimate. Next step, we have to construct the likelihood function, which is the product of the PDF function from the first part. So this is basically the multiplication of the function of the PDF. Okay, and then from that product function, we're going to take ln of the function, and then the last step, we're going to take the derivative of this ln function in order to get the estimation of the particular parameter. Let's look at an example here for the estimation of MLE for the exponential distribution. Okay, this is the case where we don't have censoring, where this is the complete data case. Okay, for the first step, we have the product of the function, which is the PDF. Okay, so we replace the PDF here, ft, according to the exponential distribution, whereby it given by lambda times the exponent into the power of negative lambda ti. So we will multiply this from the first data I equal to 1 until n. So we have complete n sample data. And then from this, we obtain the product, which is lambda into the power of n, and this lambda times total t. Okay, from that, here we take the ln function. Okay, so ln on both sides, this is log likelihood, this is likelihood, so this is the ln. Okay, so take ln both sides, so now n times the ln lambda, and then the exponent here cancel out because we take ln. So what remaining is lambda times the time, total time. Okay, this is the total time of failure. So from this, we will taking the derivative. Okay, so because we only have one parameter, so it is on the theta. Theta now is the lambda in the case of exponential distribution, and then we set the derivative is equal to 0, and then we bring the lambda on the other side. Okay, so leave it only lambda here. So what remain here is n divided by total failure time. So this is how we obtain the estimation of the lambda previously. So you have to remember that this formula is only applied for exponential distribution, because lambda, where it is the exact rate which is constant. That is why we can estimate the point estimate of the lambda, which is it does not depending on the time, and then it is constant, so we have just total up the failure time and then n divided by the total time failure. Let's look at another example. It is for type 2 sensory data. So remember that type 2 sensory data, we know in advance how many failure that we want to record. So now, okay, let's say we have T1 until Tn of the observation, or the n from the n sample. From here, we know that we can divide it into two, which is the censored and uncensored. Okay, so 1 to n here is the complete data set. And then we can sort it into the ascending order, which is T1 here in bracket is the smallest, which is the lowest time fail. And then followed by the last one, which is TR. So this is the last observation that we're going to record. We will split the joint probability density function into two parts, which is the first part is for the complete data, the uncensored data, which is from I equal to 1 until R. So here we know the exact time of the failure. And then the second part is the censored data, which is we don't know the exact time of the failure, whereby it is n minus r. So this is the number of failure that we don't have the exact time of their failure. And then here 1 minus ft can be substituted into st. Okay. And then we know that the ft of the distribution of exponential, so we substitute into this function, and then also for the st. So here is the function of PDF and st, or the reliability function of the exponential distribution. Okay, so for the first part here, we can take out the lambda. So remain here multiplication of the lambda ti. So means that it is summation of ti. Okay, so this is the first part, and then the second part. So power here, power into the power of n minus r. So it will become n minus r times tr, because we want to simplify. So exponent here, only exponent one time. And then we will substitute the time here as the capital T. So the total time is capital T, and then we obtain the equation here. Okay, so lambda T, so T will present the total time. Then the next step, we take ln on both sides. So ln of the likelihood function. So for this one, it is constant, and then it will be, here is the r times the ln lambda, and then here exponent cancel out, remain only negative lambda t. And then next step, the last step, we will differentiate the log likelihood function here. So when we differentiate, constant is 0. Next is r, okay, ln lambda is 1 over lambda, and then lambda t is t, okay, because we differentiate at lambda. So this is what remaining after we take differentiate. So it is equal to 0. So then we bring out the lambda into this side, on the left side. So remaining only r divided by t. So r is the number of recorded failure data. So how many failure data that we have record the exact time of their failure time. So it is R and then divided by T. So T is this one. So means that we have to understand here, this is the uncensored, this is censored, and then we have to substitute here TR. Okay, TR we will depend on the time of failure on the R failure. So we substitute the time here and then we sum up this total failure time in order to find the point estimate of the lambda of the exponential distribution. Let's move to the next example, which is the type 1 sensory data. Okay, so let's represent all the data into x1 until xn. Okay, because it is time censored, so we do not know how many data that we are going to record their exact time. Okay, so we will use the indicator variable, which is the lambda here, and then wi will be the time of failure, which is we are going to choose whether it is xi or ri. Ri here is the time of the censored, which is we know in advance what time we're going to stop the recorded data. So here is the time ri. And then the indicator variable, which is the delta. So delta can take number of 0 and 1 as usual. Okay, it is indicator variable. Okay, so 0 for the time is greater than the censored time. So means that here 0 will represent the data that it is censored. So 0 for censored, 1 for uncensored, because the time is less than the time that we're going to stop the experiment. So for the combination of the omega and delta here, okay, so if the delta is 0, okay, for the case of censored data, so the omega here will take the minimum, whether it is the exact time of failure or the last time or the time of the experiment will stop. So means here for the censored, means here it will be the Ri. Okay, but for the uncensored it will be Xi1. Okay, so this is the indicator variable. So this is for censored, this is for uncensored. So uncensored means that we know the exact time of the failure. Okay, for the failure time, which is x1 here should be x1 until xn, we will divide into two parts, which is the first one for the uncensored. Okay, so this is uncensored y, and then censored is z. So for the uncensored, from I, which is here 1 until m, and then continue m plus 1 until the last observed data zn. Okay, so this is the last one, which is we don't know the time of the exact failure. Okay, so follow the step by step of the MLE. So first we construct the joint PDF of the expected distribution, which is the exponential distribution. So here we denote the first part is for the uncensored, second part is for the censored. So for the uncensored, it is start from I equal to 1 until m. So this is the PDF, and then this is the RT, means that it's still surviving, right? Okay, so that is why here we use the RT. So it will start from m plus 1 until the last data, which is n. So it is continue here from 1 to m, and then m plus 1 until n. So we split into two parts, which is from 1 until n. And then we will use the omega and delta notation. So for the uncensored part, we will into the function of the PDF will taking the power of delta. Delta can be 0 or 1. And then here for the censored part, 1 minus delta. So we know that here delta will be 1 because it is uncensored. This one will be 0 because it is censored. And then omega can take whether X or Ri just now. Okay, so means that here for each data, it can take either one of these function. Means that the indicator will define which function it will take. If it is the uncensored data, so will be take the first PDF. Okay, otherwise it will take the RT here, okay, for the censored. Okay, so means that, okay, let's say the delta I is equal to 1, which is it is uncensored data. Okay, so delta here will be 1, so we have the function here of the PDF. But here when we substitute the delta into 1, so 1 minus 1 is 0. That is why this function, we don't have this function. Okay, we just have this function. Means that for each data, it only can take either one. Okay, so let's say for delta I equal to 0. So 0 here means that we don't have this function, okay, because it is into the power of 0. And then here 1 minus 0, so it equal 1. Means that it will take this function instead of this function. So this indicator variable will be determine which function that the data will take. Okay, then you can try on yourself the step by step. Okay, the following step, which is this is just for the product function or the joint probability, and then followed by the log, and then differencing, and then we take differencing of the lambda, the expected parameter that we want to estimate. And lastly, for the t, okay, that will represent the failure time, you will obtain summation of delta I times wi, this is the omega, then summation of 1 minus delta I times the omega I here. Okay, so this is the part of this one, okay, for the censored, and then this one is for the uncensored. So means that for each data, it just take one summation, which is delta will indicate them. Okay, so means that if this one, it will take the xi, the exact time of failure. For this one, it will take ri, means that the time that we stop the experiment. Okay, because this is type 1 censoring. Okay, so this is the summation of time. So eventually last, we will prove that how we get this last estimation of the lambda for type 1 censoring data. Okay, whereby it is defined as R, number of observed or the recorded data, which is the exact time that we know. Okay, how many of them we have recorded, and then divided by the summation of failure time, which is this one is for the uncensored, this is for the censored. Okay, TR is RI just now in the MLE. Okay, that's all. Thanks. Assalamualaikum.